So now that we've got the basics of the binomial theorem, let's extend our knowledge out beyond just the positive integers. These look terrible, I know. There's no convenient way or nice way to just boil this down to a summation. Actually, you'll see what the summation would look like later, and you'll understand why I didn't give it to you. However, you don't have to memorize these. They appear in the formula booklet that you'll get with the IB exam. They're also on the 2-page formula sheet that I gave you. So you don't have to worry about memorizing these, which is great. We can expand our knowledge out to negative powers and to rational powers. So we'll start with negative powers, and for negative powers, we can kind of follow this whole idea here. So to expand 1 minus x to the negative n, for some, it says positive integer n, that's because the negative's already there, right? So let n equal 2, I get negative 2, that gives me the negative power. And then this condition here, this negative 1 less than x less than 1, we're not going to worry about right now. Just accept that it has to be there kind of as a formality for the time being, because this can only be explained with later calculus, with like integral calculus, sequences, and series. This is end of calculus 2, not anything we'll be getting to in year 1. So for now, just accept that it's there. I think later in the curriculum we learn why that is, and if not, it's something that you would explore in college. So here's our formula. If you notice, it's actually an infinite series. So I would have to tell you where to stop. And this is what we notice. We have 1 plus nx plus, and then you start to see the formula. N times n plus 1 over 2 factorial and x squared. And this pattern continues. And what you might notice is that the power on x and the factorial you take match, and that actually winds up being true up to our general term as well. So that's something we'll note. The power and the factorial match. We notice that we have the product of, I'm going to use a different color here. We have the product of some number of n plus 1 consecutive integers from n. And there's as many factors in that product as we have power, and it just goes up to 1 less than the power, right? So we notice that there's 1 less than the power, but we also notice that there's as many factors here as the degree. So the number of things being multiplied, the number of factors, equals the degree of that term. Right? There are 2 factors for the second degree. There are r factors here for term of degree r. For rational powers, the principle still kind of applies. Actually, let me change this color again. The principle, although this is still a gross looking formula, very much is the same here. Again, this distinction has to wait. This is a later calculus thing. Not much has changed. So if I compare the negative power expansion to the rational power expansion, obviously I now have a rational number up in the exponent. But I notice a lot of the things still match, right? I should still notice, I'll still kind of use the colors differently here, that the power and the factorial match. And I probably still notice that the number of factors I have is the degree of the term. And I also notice that I have this whole 1 less than the power thing going on, right? I have, if I'm on x squared, I'm going up to alpha minus 1, right? So I have the whole 1 less than the power again. over here, whoops, that's not my highlighter, over here, again, the number of the factors matches the degree of the term. That's true everywhere, I just needed a space to write it. And the other thing that we notice is all the addition signs within the term, so addition within terms in, I'm just going to label this equation number 1. I'll label my negative powers equation number 1. So the addition within the terms in equation number 1, if you notice, it's all turned to subtraction and vice versa. Right, my addition here is now subtraction. My addition here is subtraction. My subtraction here is addition. But it is a series, so all of the addition between terms remains. All right, so again, this is an infinite series, which means I have to tell you where to stop. There is no great way to write this out in general. Actually, that would be the summation for, if I can pick it up without picking everything else up, my first one. And my second one would look quite similar. Should be a division bar there. Right, and so you can kind of see why I didn't just give it to you written out that way, because I've got the product within, I have the product within the summation, and it's just not great. So while there is a way to do it in general, let's not worry about that. Let's just ignore that. Let's just get rid of that. And let's try some examples. So expand each of the following up to the term written in x cubed. So I have to give you the stopping point. So square root of 1 minus 2x, and your first thought might be, well, this doesn't fit anywhere. And it does. So I can write, as you might remember, I can write square roots as rational powers, right? The square root of x can be written as x to the 1/2. So this whole term can be written as 1/2, 1 minus 2x to the 1/2 power. So this is a rational power, so I'm going to use my second formula here. And actually I'll leave both on the screen just like that. So 1 minus 2x to the 1/2, and I want to go up to x cubed. So still starts with 1. And then alpha x. So alpha, if you noticed up here, was my power. So my power is 1/2. 1/2 x plus 1/2 times 1/2 minus 1, which is negative 1/2, over 2 factorial times x squared. And then that pattern continues, so I'm going to have 1/2, subtract 1, subtract 1 again. Stop. I've got x cubed, I'm good, we're done. Stop there. Let's simplify this mess. So I've got 1 plus 1/2 x plus, let's see, this becomes negative 1/4 over 2. We'll come back to that in a second. And then I'm going to have, whoops, that shouldn't be 3/8, that should be 3/2. Positive 3/8 over 6. And I can deal with those complex fractions. So that's 1/4 divided by 2, or times 1/2, right? So 1 plus 1/2 x minus 1/8 x squared, and then I get 3/8 divided by 6, which is the same as multiplying by 1/6. So I'm going to get 1 over 16. Assuming I did that correctly. X cubed. And there's my expansion. And I could actually continue this expansion. This is, again, something that you would see later on in integral calculus, in Calc 2. So we're not going to really get into the nuts and bolts of this, but for now you should just know how to write this expansion. And we can do the same thing for part B. Again, right up front, it doesn't really look like I can do anything here, but I can. Remember that 1 over x can be written as x to the negative 1. So 2 over 1 minus 3x can be written as 2 times 1 minus 3x to the negative 1. When we're doing this expansion, we can actually just leave the 2 out of this until later. Right? It would be 2 times my expansion. So let's do that now. Again, if we go back to my formula up here, starts with 1 plus nx. 1 plus the degree, which was negative 1, times x. Plus, oh sorry, just n. So I don't want the negative. I just want the number. So 1x. So we want to be really careful there. N is not the negative, so ignore the negative. And then, let's reference it again. This is where I want to add my consecutive factors in. So 1 times 2 over 2 factorial. Oh, I realize I'm messing this up. So the other thing we want to be careful about is when we have an x, I want to take that whole thing with me, right? Because it's 1 minus x. Yeah, so I want to take that 3 with me too. So I should be careful here to make sure I'm writing 1 times 3x. So over here we'd have 3x squared. And then I'd have 1 times 2 times 3, right? My consecutive powers again. Sorry, consecutive factors again. Times 3 factorial. And then I have 3x cubed. So I just want to be careful and make sure I'm taking the entire thing in that second term along with me for the whole problem. So now we can go ahead and simplify this. This is going to be 2 times whatever this simplifies to. So I have 1 plus 3x plus, well, 2 over 2 is just 1, right? 2, this is equal to 2. This is equal to 2. 3 squared is 9, so 9x squared. And then I get, oh, this one's an interesting one. So 1 times 2 times 3 is just the same as 3 factorial, so this all cancels out. And I get 27x cubed. And I could also take care of the distribution as well. So again, you don't have to necessarily know this formula inside and out. You don't necessarily have to have it memorized. I mean, you saw me go back and reference it myself. But you should at least know how to use it and what the notation means, right? You should be able to use it, you just don't necessarily have to memorize it.